So hello everyone, today we'll be discussing about disjoint set union, which is a popular data structure used for solving many good competitive programming problems as well as it's quite helpful in OAS as well. So what's exactly disjoint set union and how can we use it for our benefit? So disjoint set union is basically a better way to find stuff and unite stuff. There are two operations. There are two operations. One is unite. Let me zoom in a bit. Yeah, unite, which is also known as union, or find, sorry, not or, and find. So there are basically two operations. One is union, second is find. What are these operations? What are these operations for? As the name suggests, if there are, let's say, two graphs, like two different components, these are said to be two disjoint sets. Like they represent two disjoint sets. How many of us know that sets can be represented by graphs? We have studied about it in graph theory that uh, each graph represents a disjoint set. Connected graph, each connected graph represents a disjoint set. So these two are representing some disjoint sets. If I want to find which of them has a red node, which of them has a red node, how can I do it? How can I do it? I would run DFS on both of them, or BFS. I would run BFS or DFS on both of them, and I would come to a conclusion that okay, graph A or disjoint set A has the red node. But can I do it more optimally? Yes. How? I can do this by the DSU data structure, which basically stores something like this. Okay, this basically stores something like this. So how many nodes are there? 1 2 3 4, 1 2 3 4. So the red node would be here. Okay, it stores all the stuff in the form of a tree. You can visualize it as a tree, but it's some sort of an array, you can say. At the end of the day, it's some sort of structure like this. Now let us say that the parent of this is a blue node, and the parent of the head node of this, or the root node here, is the green node. I can basically say all the nodes with parent green node is one disjoint set, and all the nodes with their parent as blue node is another disjoint set. Now can I do this in O of 1? Can I do this in O of 1? I can simply look at this and say, okay, I can simply look at this and say that if red's parent is blue, then it belongs to set A. If red's parent is green, then it belongs to set B. I can simply say this, right? I can do this thing in O of 1. I would just check the parent of this, and I can say this in O of 1. Okay, coming to the union operation. Okay, so union can be optimally done by merging small to large. Like if you merge it this way, this is optimal. But if you merge small to large, what would happen? You would get extra levels, right? You would get extra levels. That's the problem. So union always takes place small to large. This thing is called union. Okay, this thing is called union. So let us write the code for, okay, let us understand the problem and how can we apply disjoint set here. Okay, how can we apply disjoint set here? Let's read the problem and understand. You are given a weighted tree consisting of n vertices. Recall that a tree is a connected graph without cycles. Vertices ui and vi are connected by an edge with weight wi. You are given m queries. The ith query is given as an integer qi. In this query, you need to calculate the number of pairs of vertices u and v, u less than v, such that the maximum weight of an edge on a simple path between u and v does not exceed qi. So qi acts like a barrier. Okay, qi acts like a barrier. After qi, if you find some other edge with some other weight which is greater than qi, you cannot basically take it in. That's what the question says. So in simple terms, can I say it in this way? Like you want to find how many pairs of cities can reach. You want to find like how many pairs of cities can reach each other using only roads, like only edges that are easy enough. Like their distance is not too high, not more than qi. Okay, this is a simpler version to say. You just want to find out the paths whose weight is less than qi. Okay, sorry, you want to find how many pairs of cities have this. Fine. So now let us think of the intuition. Let us think of the intuition behind this problem. Okay, so just imagine that the tree starts with all n vertices but zero edges. Okay, there are all n vertices but zero edges. That means each edge is a disjoint set. Sorry, each vertex is a disjoint set. Each vertex is a disjoint set. Let us assume this. That means it's like some n isolated islands. It's like some n isolated islands. Okay, so can I say that if a pair U and V, if a pair U and V is connected by edges with weight less than or equal to some 5, okay? There's a particular edge U and V. There's a particular edge U and V, okay, U and V, which is connected by a weight 5. U and V is connected by a weight 5. So they are definitely connected. Like if we allow the weight to be 10, if we allow the barrier, which is nothing but the Qi, okay, if I allow this to be 10, I can still take this edge, right? I can still take this edge, right? The edge weight is 5. I can take it when it's 10. I can take it when it's 11. So can you observe some pattern here? When it's less than 5, when it's less than 5, 1, 2, 3, 4, it's no. Then it suddenly becomes 5, 6, 7, 8, so on. It becomes yes. So can I say that there is some sort of monotonicity? There's some sort of monotonicity. This particular sequence is monotonic. Can I say this? That means as Q increases, the number of valid pairs also increase, isn't it? As Q increases, if Q becomes infinity, all the pairs are valid, right? As Q increases, the number of valid pairs also increase. This is an observation. Let's write it down. So I can write, let me take it. Let me take the question. So what are the observations? If Q increases, the number of valid pairs also increase. Okay, due to monotonicity. If Q increases, the number of valid pairs also increase. Okay, do you know what's monotonicity? Monotonicity is nothing but this thing. After a particular sequence, it's all takeable. It's all takeable. So if the weight is 5, if it's sharp 5, you can only take till here only. Okay, when the weight was 5, you can only take till here. When weight goes 6, you can take this whole thing. When a weight was 7, you can take this whole thing. Okay, so that particular thing is monotonic. Okay, monotonic is basically like after a particular point in the sequence, the answer to something becomes yes all of a sudden. Then it remains yes for all the remaining stuff after it. Okay, like yes till here and no after this, or else it would be no till here and yes after this. These kind of things are known as monotonic. Usually we apply binary search on these kind of sequences, but don't get misguided. Like it's not a binary search question. Don't worry about it. Because initially it's not monotonic. If it was monotonic initially, we could do some searching and stuff. Okay. So if Q increases, the number of valid pairs also increase. This is our first observation. Fine. Now, when you add an edge between two separate components, let's call them some component A and component B. Let's call them some component A and component B. Let's say there are two different components. There's a component A and there's a component B. They are not connected. And if you want to add an edge between them, okay, when you add an edge between two separate components, every single node in A now can reach every single node in B, isn't it? Now there's a road in between them. Okay, so there's a road in between them. There's a road in between these two cities. So the people of this city can now move to this city. We made a bridge, right? We made a bridge here. So now people of this city can reach all the nodes of this city, right? Isn't it? So there, now we created a path. If component A has size some A vertices, now let's say this component has some size A vertices. Let's take it not A, some X vertices, because the component name is also A, so it's confusing. Fine. So if the component A has X vertices and component B has Y vertices, component A has X vertices and component B has Y vertices, the number of new pairs that can be formed. What's the number of new pairs that can be formed here? Okay, so the number of new pairs formed by joining exactly X vertices and Y vertices, basically X cross Y vertices. The total number of pairs in a component of size K is, if the size is K, then it would be equal to KC2, isn't it? Isn't this KC2? From K, like X vertices and Y vertices, if there are, let's say, total K vertices, from these K vertices, you're choosing two vertices and making an edge, That means you're picking two vertices from K vertices, which is nothing but K choose 2. Okay. So the math stuff is done. We know it's monotonic. Now, how to actually solve this problem? Now we can easily solve this problem since we have made most of the observations. Now we are sure with counting the counting logic, which is KC2, the number of pairs we can count easily, and we are sure with the merging logic. Now DSU data structure is perfect here because it will allow us to build the tree dynamically, isn't it? Whenever you unite the tree, whenever you unite two nodes, basically, you're doing this only, right? You're performing a union, right? So DSU would allow you to do it, to build the tree dynamically by sorting both the edges and the queries by weight, since they are monotonic. We only add edges when they are allowed. Okay, like if we hit this barrier, till here it was no, sorry, it would be yes. Till we hit this barrier, we would keep adding them, isn't it? Okay. And another advantage of DSU, we haven't implemented DSU yet, but it's very easy to grab out size of a component. Like you can grab the size of this component very easily in DSU. Okay. And the total size would just become the size of B added, isn't it? So now let's get started. So, okay, we have observed that it's monotonic, it's fine. Let's take the input N and M, right? What was the next thing after this? Edges, isn't it? Was it edges? Yeah. Let's make a struct edge because it has weird properties. Okay, so one important thing I would like to tell you is never be afraid of creating weird data structures all by yourself. It's very common, trust me. That's how it works. Never think that, okay, this thing is getting weird, this might not be the right approach. Who knows? Like the problem setter sometimes may ask you weird stuff also. In some of my problems, I've even created some really unimaginable stuff, like structures with pairs inside and all those things. So it's very normal to create weirdest data structures. Okay, so uh, let me give a recap of the question. You'll be given a tree, sorry, you'll be given some edges, and you need to like count the number of pairs whose weight is less than qi. You just need to count the number of pairs. That's the question. That's the question. What's our observation? Our observation is that, okay, so the basic idea is that if I want to like check it, what's the maximum weight of an edge on a simple path between u and v, which does not exceed qi. If I want to check this, if the edges are sorted based on their weights, that means if they're sorted in ascending order, in that case, I can check one by one. I can check one by one. What's the maximum one? I can check this, right? I can check one by one if they're sorted. So my first approach would be like, okay, I have this sorted. I'll be going through edge 1, edge 2, and so on. I would go this way, like edge 1, edge 2, edge 3. All of them are sorted in ascending order until I hit a barrier. After this, all of them would be greater than Qi. So this would form a monotonic sequence. And since Qi is also a monotonic sequence, since Qi is also a monotonic sequence, like if we have already discussed this example, right, where Qi was 5, some edges were getting included. Those edges would again repeat in when Qi would be equal to 10, isn't it? So as Qi increases, the number of pairs also increases. So it's a monotonic sequence. Now, uh, that means I should sort. I should sort the edges based on their weights. So I would sort edges dot begin to edges dot end based on their weight. So I would have to write a comparator edge A, edge B, right? And need to return A's weight should be less than B's weight. Fine. So we have written a custom comparator to sort on basis of weights. Now we have to sort, not we can sort, we have to sort queries also because they are also monotonic. So it would be quite easy. It would be really quite easy, right? If it's a monotonic one, I can simply maintain an aggregate from smaller values to larger values, right? So to maintain that aggregate, I need to sort the queries also. It would be a huge optimization. I cannot miss it. But after sorting queries, can I do this? Can I do this? You need to print it for each query. You need to print the answer for each query, right? You need to print the answer for each query. So if the query's order changes, isn't that a trouble for us? So how about storing the order? How about storing the order of queries? How about storing the indices? I can just do it by vector pair int or an unordered map. Okay, either you can use a vector pair int or an unordered map. Both are fine. I need to store the index of queries, so I would simply do it like I would take the input of queries of I dot first, and the index which would be in the pair second one, it would be equal to queries of I dot second, which I will mark it as I. Fine. Now I can sort queries dot begin to queries dot end, and pairs are sorted based on their first elements. Pairs are sorted based on their first elements. All right. So we need not worry about writing the comparator. So now coming to the main thing, we have made the observations that both of them are monotonic, and we can comfortably solve this problem by sorting the edges as well as queries. Now, coming to the actual calculation part. Now I need to compute the result for every query. I need to compute the result for every query, right? I need to compute the result for every query for all m queries. Now, let's take the count of current pairs is equal to 0. Current pairs initially are 0. I don't know how many pairs are there which satisfy our condition. And let's take the current edge to be 0 as well. Current edge to be 0 as well. Current pairs is 0, current edge is 0, and this was our approach, right? We would traverse till we hit a barrier. So we would traverse till we hit a barrier for all m queries. So the barrier is equal to queries qi basically, which is nothing but queries of I dot first, and we should also store the index because we need to like assign the count to it. So index would be equal to queries of I dot second, and with this result of that particular index would be equal to the count. And in between this, we would do some computations. Let us observe. Okay. Compute the number of pairs. How to compute this number of pairs? While my current is less than n minus 1 and edges of current dot weight is less than or equal to my barrier. I cannot go beyond the barrier, right? I cannot go beyond the barrier as discussed. U would be equal to edges of current dot U, and int V would be equal to edges of current dot V. Now, what do I exactly want to find? What do I exactly want to find? What do I exactly want to find? So I want to find the number of pairs, and they would be equal to size of a component A multiplied by size of component B, isn't it? It would be equal to the size of the component A multiplied by size of the component B if both of them are disjoint. Okay. If there are two disjoint sets A and B, how many edges can you draw? Okay. If these are the two edge, what am I saying? What were they? Disjoint sets, yeah. If it's A, B, C, D and E, F, G, you can draw 3 from A, 3 from B, 3 from C, and 3 from D. That means you can draw 4 into 3, which is nothing but size of A into B. So these many number of pairs exist. These many number of pairs exist whose under the barrier. Under the barrier, these many number of pairs exist. So count plus equal to, let us assume there's a black box named DSU. DSU is a black box for us. Okay. It gives you, later we'll see the implementation also. Okay, later we'll see the implementation also. So let's do 1LL multiplied by size of A. To get size of A from the DSU, you would basically do DSU dot SZ of what's the component? The component is to get the component in which U is present, to get the parent in which U is present, you can do A is the component in which U is present, so you would do find the parent of U, which is find of U, and int B is equal to find of V. Okay, A equal to find of U and B equal to find of V. When you take this disjoint set, you just need to multiply the sizes of A with size of B, isn't it? And now you can unite, now you can simply unite U and V. And with this, okay, you should be doing this only when they are not already connected. So how to check if they are connected or not? If A not equal to B, that means both of them don't have the common parent. In that case, they are not connected. And let's move to the next edge. Okay, with this, the result array would be completely filled with the right values. Now, all we need to do is print the result array, cout result of I, done. So, okay, we forgot to actually make a DSU. So let's quickly make a DSU. Let me tell you how to make a DSU here. You would need a struct DSU. This is a very standard template. So you would need a vector int parent, and you would need a vector int size. DSU would take n nodes, and initially let us assume that you need to mark the parent for all the n nodes. So let it be n plus 1. And initially, let us assume that every node is independent. All the nodes are disjoint. Like it's n connected islands. Let's take it this way. There are sorry, not connected islands, n isolated islands. Let us take it this way. No node has a connection in between them. In that case, what would happen? I less than n minus 1, I plus plus, sorry, not n minus 1, n plus 1, I plus plus, and parent of the node would be equal to itself. A node would be itself's parent because every node is isolated, none of them is connected. And and the size of the components, all the components are consisting of only one node. So all the components would have a size of 1 initially. Okay, we have made a DSU constructor now. Now coming to two operations. One would be int find, in which you can find a node, and int unite, or else you can take it as bool unite, in which you can basically unite two nodes u and v. Okay, all the stuff is visual. We don't really manually unite or do stuff. It's just visualization. The visualization of a tree is I hope very simple. Okay, whatever is happening in the array operations, please visualize it as a tree. Okay, if parent of node is itself, is the node itself, I want to find it, right? I want to find it. In that case, return the node. It belongs to the node belongs to a disjoint set in which the head node is the node itself. Otherwise, if the node has a parent, then find its parent's parent. Basically, find the parent until you reach the root of the node. You just need to find the root of the node. That's what the find operation means. You are just finding the root of the node. Node belongs to a tree. You are just finding the root of that tree. Fine. You are just finding the root. Now coming to the unite operation. Sorry. Coming to the unite operation. So unite, as said earlier, unite always takes place from small parent to the large parent. So let's take a small parent, a small disjoint set which is nothing but find of u, and a large disjoint set which is find of v. If both of them don't belong to the same, ones, there could be a chance that they belong to the same disjoint set. But if they don't belong to the same disjoint set, in that case only you can unite them. Otherwise, you would return false. Now, if okay, we are assuming that u always belongs to the smaller one. No, wait, u always belongs to the larger one. And let us take v always belongs to the smaller one. Okay, we are merging u to v. Sorry, we are merging v to u. Okay, we are merging small to large. Okay, so if you want to merge small to large, but not necessarily every time you would belong to the larger one and we would belong to the smaller one. This is not always possible, right? The user might give any kind of inputs, or we may receive any kind of inputs. So if size of large is smaller than size of small, swap large and small, so that large always stores the larger one, small always stores the smaller one. And parent of small, we are merging small to large, so parent of small becomes large. And size of large, since now small is added to it, size of large becomes size of large plus size of small. So this is the basic template of disjoint set union. At the end we return a true. Fine. So I hope the code is clear. Let me reiterate. We have a black box named disjoint set union whose job is to give you the accessibility to operations like find, unite, and size. Okay. You can find the parent of a tree. You can find or a graph. You can find which set does it belong to, which component does it belong to, using find operation. And unite, you can unite, dynamically build the tree. You can unite two different disjoint sets. That's about the black box. Coming to the problem asks you, the problem sets a barrier qi which is a query, and you cannot pick some edges which exceed the value qi. Okay, the question is very simple. You need to find the number of roads between two cities whose distance is less than qi. Okay, now to build the tree dynamically, we use this disjoint set, and uh, we can also get size out of it. So we can simply get the number of pairs. Okay, and how did this come up? Like size of a into size of b. The logic is here. You can make these many edges in between them. So we just compute it. Why did we sort it? Because the both the sequences are monotonic. If queries is less, let's say some k, q of I is let's say some k, and you can, let's say you can take some p number of pairs. When the query of I becomes k plus 1 or 2k, you can obviously take more amount of pairs. So it's a monotonic thing. And since we are waiting for the edge to hit the barrier, we are waiting for the edges to hit the barrier, we are moving rightwards. That's why we have sorted the edges also. Okay, so this is the basic implementation. It should pass all the test cases. Expected primary expression. So I guess we forgot to declare this DSU structure. So let's declare it somewhere here. DSU DSU equal DSU of n nodes. DSU here and DSU. Sorry, my bad. Okay, so that's it. Let's try to run it once again. It is supposed to work. Looks like we have messed up somewhere. Find we are doing. Where are we doing find? It's obviously an integer. What could be the error here? Okay, this thing here. DSU.find. DSU.find and miss some semicolons here. Okay, this should be parent of node equal to. Now let's check. Still an error. What could possibly go wrong? So, should be n minus 1. Yeah, passed. Now let's run all. All of them should pass. Yeah, all of them passed. Now let's try to submit this. Yeah, accepted. Now let's move to the next problem. That was a nice one, right? I hope it was quite educative. Here we came across three ideas. First thing is that monotonicity, and also the greedy idea of this barrier thing. Like, why are we sorting? To check for the maximum till it hits the barrier. So this idea was great, and obviously the DSU data structure. Coming to the next problem, let's read it. Berlin government decided to improve relations with neighboring countries. First of all, it was decided to build new roads. Building new roads, obviously DSU. Building dynamic paths, obviously it's a DSU question. It was decided to build new roads so that from city of Berlin and neighboring countries, it became possible to reach all the countries. It became possible to reach all the others neighboring countries. It became possible to reach all others. There are n cities in Berlin, and neighboring countries in total are exactly n minus one two-way roads. Because of this fight, because of the recent financial crisis, the Berlin government strongly pressed for money. So to build a new road, it has to close some of the existing ones. Every day, it is possible to close one existing road and immediately build a new one. So you can close one existing road and build a new one. Your task is to determine how many days would be needed to rebuild roads so that from each city it became possible to reach all the others and to draw a plan of closure of roads and building of new ones. Okay. So what does the problem say? What does the problem say? In simple terms, you have n minus one roads. You want everyone to be connected. You want every other country to be connected. If your current roads form a cycle, you have a useless road, right? Basically, it's taking you to the same point again. So that particular road can be removed. Since we have a shortage of money, that particular road can be removed. It's a useless road if it forms a cycle. That clearly means we need to build a tree. That clearly means we need to build a tree. Okay. You cannot move elsewhere to connect an isolated city, right? So coming to the intuition, actually this particular sentence is enough. So there's a tree with n nodes. You must have exactly n minus one edges and no cycle side. If you try to add an edge between you and v, and they are already in the same component. Let us assume they are in the same component, and you try to add an edge between them. That particular edge would create a cycle. That means it's some sort of redundant stuff. It's a repeated stuff. It's a repeated route. It's a redundant route. We can cut it without disconnecting anyone, isn't it? Without disconnecting anyone, you can cut out a road which forms a cycle, isn't it? And after looking at all the n minus one roads, you have some k separate components. Let us assume you have some k separate components, which you can treat it as islands, like they're not connected. You need k minus one new roads. You need k minus one new roads to link all of those islands together, right? If there's a tree with n vertices, it takes n minus one edges to link all the tree, like all the nodes and form a tree. So to form a tree with k nodes, you would take k minus one edges. That means k minus one new roads altogether. Okay. So the strategy would be every time DSU finds a cycle. So in this problem, we'll understand how does DSU help us to find out the cycle. Every time DSU finds a cycle, put that road in a pile, let's say to be removed pile or the redundant pile. Identify the root of each island. Okay, identify the root of each island. Use the roads from your to be removed pile to connect roads of these islands. This would be the strategy, isn't it? Okay. So DSU is a standard tool for cycle detection. Let us understand how. So let's take a water break. Okay. Uh, First line contains number of cities in Berlin and neighboring countries. Next n minus one lines contains description of roads. Fine. So how about not taking this? Okay, let's take it, no problem. You can do it without taking a separate array for roads also. Let's not take it. Unnecessarily, we need to make a new structure and stuff. We need to take n minus 1 rows. DSU of size n. Okay, so each n minus 1 line would have n minus 1 lines, each of them would have u and v. So let's take it. If DSU of, okay, wait, let's unite at the same time. Okay, we need to unite them at the same time, and this particular edge creates a cycle. So you would do keyboard errors. Let me disconnect this keyboard and use actual laptop keyboard. Okay, let's have an array named redundant of size. Okay, size is unnecessary. We don't know what would be the size. And redundant dot pushback u and v. This condition means it's a parent. That means it's the root. So roots dot pushback. If a particular node is itself parent, it's the root. So we would push it back into the roots. And okay, we need, how many new roads do we need? How many new roads do we need? We need, okay, as discussed in the problem, number of new nodes is equal to number of disjoint cities or countries, whatever was given in the question. It's unnecessary for me. Whatever the disjoint components, else let me call it components. Number of disjoint components minus 1, because you're forming a tree out of them. Without cycles, a graph is called a tree. So I would need number of disjoint components minus 1. Okay. So the number of disjoint components is nothing but number of roots. So I would just do roots dot size minus 1. And I can just simply do these many redundant cities. I would need redundant of I dot first fine. This is what the answer would look like. Okay. So let's reiterate through the problem. What does the problem exactly state? Berlin government decided to, okay, it decided to make roads between new countries, neighboring countries. There are n cities in Berlin and neighboring countries is totally uh, and neighboring countries in total, including neighboring countries, there are totally n cities and exactly n minus one two-way roads. Financial crisis and to build a new road, it has to close some existing roads. And how many ever existing roads you close, that many new roads you can make. And uh, every day it is possible to close one existing road and immediately build a new one. So you need to close the redundant roads and build a new road. Your task is to determine how many days would be needed to rebuild roads so that from each city it became possible to reach all others. Okay, so I need to output t. What's the least number of days? What's the least number of days? The least number of days would be equal to the total number of roads that has to be built. So number of new roads is equal to number of new nodes, which is nothing but number of disjoint components, which is, did I write roads? This is roads, sorry, not nodes, it's roads. Number of new roads is equal to number of disjoint components minus one, because we are supposed to form a tree. And each line should describe one day in the format IJUV. It means that roads between cities I and J becomes closed. In our case, redundant roads become closed and roots of I and roots of I plus 1 form a new road. And to this, let's add the disjoint set thing. Okay, we have some error here. Has no member named first. Redundant of I. Okay, so it should be 0 instead. 0 and 1. Okay, passed. This one failed. Gives a different answer. But I still hope the logic is absolutely right. So let's try to submit this. This should get accepted. I mean, there could be multiple ways. There could be multiple ways. Roads in Berland. Let's paste our solution and check it. Wrong answer. So let's see what's wrong here. So looks like previously I submitted it for the wrong one. Sorry, the question was wrong. So thank you everyone. That was for today. I hope the session was clear.